essentially go above the maximum and below the minimum values we're seeing in a data set. What if I ask you for the probability that the return next year is exactly 4.83%? And that's a very specific number. It seems really unlikely to me that I'm going to say, you know, that seems pretty small, right? But yet, it's a value we saw in our data set, and when we approximated the distribution, we gave it a probability of 1 over 88 of occurrence, which is more than 1%. It's not completely trivial. So that seems a bit weird. So I want to suggest that the way to think about this is you want to think about the probability the return is in between 4 and 5%. So the biggest change in your mental thinking here is when you're dealing with discrete cases, like a dot. You're saying there's some probability it comes up 1, there's some probability it comes up 2, there's some probability it comes up 3. And I'm suggesting that when we're thinking about continuous random variables, you never want to think about the probability that the market is going to return exactly 4.83%. It seems more helpful to think about it as the probability we're going to return somewhere between 4 and 5%. So rather than thinking about the continuous case where you're thinking about a probability a specific number comes back, think about it as the probability that a return or what comes back to you is going to be in some interval. And that's probably the biggest shift in the thinking. So assigning a probability to an interval actually somehow seems more sensible in a lot of cases. Continuous probability distribution assigns probability to intervals, not point values, and it can have an infinite upper bound or an infinite lower bound. We won't actually see that until next Monday, but that's also part of where we're going. So I think the best way for you to experience a continuous random variable is for you to make it yourself. So that's going to be my first small exercise here. We've done several examples in class where you're using data to estimate CDF. And so far we've always done this with the assumption that the underlying random variable is going to take on some subset of discrete values. But it may not always be the case. And let's think about the rand function in Excel. Supposedly that function is going to return something between 0 and 1. And each observation from rand can be viewed as a sample from a distribution. I should be getting back something between 0 and 1. There should be some distribution of what I'm getting back. There should be some probability I get back something between like 0.4 and 0.6. So I want you to figure that out for me. And so let's think about this. There's an observation number, and you're going to type into Excel equals rand. And it's going to come back as something. And then you're going to do your second observation. And you're typing equals rand, and it's going to come back as something. And you could keep doing this. And if you keep doing that, you can produce a histogram plot. You can produce a histogram plot. You can try to think about what your CDF function is. And that's my question to you for the next 5 minutes. Tell me what my distribution should be for the rand function in Excel. What is your best guess at that?
Something roughly around, if you structure for the histogram begins from 0 to 1 in intervals of 0.1, they should basically be distributed somewhere around, you say 100 observations, 10 to 15 each day.
So you're thinking every bin should be equally likely. That seems like a good guess. You can verify. So I'm going to force you to verify this in the next few minutes. You know how to do histogram plots. You create your own data set, you can do histogram plot. And JP's right, so you have an idea of what should be going on here. about here is if I ask you for the distribution function, how are you going to specify to me what probability should come back for this random variable? So I've got one Excel crash.
So just histogram plot. Okay, so I see most of you have observations. Yep, perfect. Okay, so yep. Or just let Excel back in. Yeah, I don't think you want to use this. Just a range of numbers and zero and those ends are not. Thank you. Okay, so why am I having you do this? I realize we've done a lot of histogram plots. I want you to have at least gotten your hands dirty enough to have a feel that you should be getting something like that coming back. And I'm going to kind of let you control things right now. We can spend more time on this if you like. If you feel pretty comfortable that something like that is what's coming back, then then I'm fine, assuming that if you have a little bit more time, you can finish out all the rest of these. So I still see people clicking, so my read of the room is going to be give it a few more minutes. Yeah. And you know, I didn't give you bins. I didn't suggest any bins. I did it two ways. I did it one where I defined bins at every 0.05, so 0.05, 0.10, 0.15, 0.20. And I also did it where I just highlighted the observations and let Excel do the bins for me. So I would suggest that either method is fine. In fact, why don't let's do the quickest method together. The quickest method would be to let Excel do these bins for me, right? So I could do data analysis, histogram, okay, input range. Input range is my observations. I want a new workbook. I want a chart output and a cumulative percentage. I'm leaving the bins blank so that Excel does this for me, and I'm going to say okay. And there I go. Is this good? Okay, so let me make a couple observations. So one observation is that in that data set, did you see every possible number randomly returned? No, you definitely didn't. I don't care how many observations of rand you took, you didn't see every possible number there is between 0 and 1. So whatever your bins are, we're kind of viewing this not as the exact distribution, but kind of as an approximation. And JP, you said something, so let's go to I define bins. And you said, well, you know, every bin, it should be like, if it's between 0 and 0.5, it should be about 5% of the observations in there. And so that's exactly right. But I want to specify this, and if, you know, if my bin was between 0 and 0.01, you'd say 1% of the observations. If it was between 0 and 0.5, you'd say 50% of the observations. So you're getting at the fact that no matter what bin sizes I describe, they should be equally likely. Which, what does that mean graphically? It means that if I took enough observations, you're kind of thinking that all of these bins should have about the same height. And maybe even a better way to think about it is this red line is like your CDF. So this should be a straight line. And I think no matter what bin sizes you chose, this red line, you should be getting something where you really see that being a straight line. That should be popping out at you. So if you think about how do I define this distribution? Well, you know, the natural way to define it here is a straight line between 0 and 1. Okay, so one of the reasons I wanted to belabor that and I wanted you to do it is because all this stuff we've been doing on histograms and putting stuff in bins, and in a way we've been acting like we have a discrete random variable. But we can take these histograms as approximations for a continuous distribution, right? When I did that RAND histogram, RAND is clearly a continuous random variable. It takes on any value between 0 and 1. We got a histogram back, and it really informed it to us that, you know, the right distribution for this is a straight line between 0 and 1. So the way you want to think about it in the continuous case is your CDF is kind of an approximation of its probabilities. In the case of RAND, it's a straight line between 0 and 1. Your bins are telling you not the probability the random variable comes back exactly at 0.5, but it's telling you the probability you get a rand number between 0.45 and 0.5. So your bins for the histogram are really telling you something about an interval rather than one particular value. Okay, so I'm belaboring that point because that's kind of like the histograms work for both cases, you just are interpreting it slightly differently in your head. Does that make sense? Head nods. Okay, so then what is RAND? RAND is our simplest continuous random variable. And I'm graphically representing it as a spinner. So it's like I spin the spinner. This is my Vegas roulette wheel. And it comes back somewhere between 0 and 1. And it's equally likely to be anyone. So how do I calculate probabilities for that? The first thing is any continuous random variable is defined by a density function and a CDF. The CDF has exactly the same interpretation as the discrete case. So the CDF, this capital F, is telling me the probability the random variable comes back less than or equal to some value x. So let's think about what does this mean for our RAND. This F, this is my CDF, this is my straight line between 0 and 1. If I ask you for the probability that RAND comes back between 0.2, well, 0.2 is the x-axis value. I look up the CDF and I say, oh, that's 0.2. 20% of the time, RAND should come back below 0.2. If I ask you for how often does RAND come back below 0.8, I say, okay, well, here's 0.8. Okay, the value of my CDF is 0.8. 80% of the time, I come back to below 0.8. Okay, so the CDF that's actually exactly the same interpretation as in the discrete case. The thing that's going to be different is instead of going to what I call the mass function, I'm going to go to a density function. And the density function, you see, it's not like a chart output where I have certain values and each value has some kind of weight. It is just a function over this interval 0, 1. And you told me everything should be equally likely, so if everything should be equally likely, this probably shouldn't change, and it doesn't. Okay, so this is just a square. It's telling me that the frequency of every value is exactly the same. And so that's this little f. When you see a little f, it's very common to represent a continuous probability density function as a little f, and the CDFs are always represented as a big F. Okay, so little f is your kind of guide that you're dealing with a continuous random variable. The other thing to realize in this relationship is if you're comfortable with calculus and integrals and derivatives, what's happening here? The PDF, this little f, is exactly the derivative of the CDF. And you can see this graphically because this has one slope, it's a line, it's going, the rate of change here of this line never changes. So it's going up at exactly the same rate. And that slope is corresponding to this constant that's 1 here. So I take the derivative of this guy, I get this guy. I take the integral of this guy, I get this guy. And so that relationship is always true. And any valid PDF, so probabilities have to sum to 1 in the discrete case. In the continuous case, they have to integrate to 1. How do I calculate probabilities? So I've been emphasizing, I said, the main thing to think about this is, think about this as an interval. So what do I mean by that? So if I want to think about this event that the spinner lands between 0.195 and 0.205, I realize you're all gonna tell me that's 0.0. Did I do the subtraction right? Yeah. 0.01 because, okay, so it's equally likely 0.205 minus 0.195 is 0.01. Okay, so that's true for RAND, but I want to be able to at some point move beyond that. So let's think about what that means graphically. So I'm asking you for the probability that I land in this interval. How do I interpret this little f? Well, when I calculate probabilities, I'm integrating instead of adding. And what does that mean, right? What does that mean? Well, 0.2 here, I'm looking at the probability I land in a little interval around 0.2. The PDF is telling me how high that is, so sort of the frequency of occurrence of those values. Okay? So when I do this integral, it's an area under the curve. And if I look at this highlighted region, it's a rectangle, and it's got height 1, and it's got width 0.205 minus 0.195, which is 0.01. So I'm getting, oh, that's 0.01. Okay. So probability is area under the curve. Okay, and I didn't have to just restrict myself to something around 0.2. I could have said, what if I land between 0.2 and 0.8? Okay, so area under the curve here is height of 1. The width here is 0.8 minus 0.2 is 0.6. So this integral is telling me 0.6 times 1 is 0.6. That's what's happening here. If you're familiar with the calculus, this helps you. If it doesn't help you, don't worry about it. But do think area under the curve. The CDF, I could equivalently do this by the CDF, and the interpretation here is, well, this guy is telling me the probability I'm less than or equal to 0.8, and this guy is telling me the probability I'm less than or equal to 0.2. So the probability I'm between 0.2 and 0.8 is the probability I'm less than 0.8 minus the probability I'm less than 0.2, and that gives me 0.6. And it's exactly equivalent to do these calculations using the CDF function, the big F, or the PDF function, the little f, using the integrals. So it's whatever's more convenient. And it doesn't have to be continuous. I could ask you for something like the event that the spinner lands between 0.2 and 0.4, or between 0.8 and 1. And here we're saying, oh, well, these are two disjoint events, so I could ask for the probability I land between 0.2 and 0.4. So that's this guy. Plus the probability I land between 0.8 and 1, that's this guy. And so that gives me 1 minus 0.8, that's the probability I land between 0.8 and 1. This one's the probability I land between 0.2 and 0.4, so 0.2 plus 0.2 is 0.4. You can do that either this way, or if you think about it like, oh, there's these little integrals under the curve, and I need to add it. Okay, the last thing I want to say about this interpretation is, when we thought about the discrete case, and I told you what probabilities each value took on, it always had to be between 0 and 1. So the thing that's interesting about the PDF is it's not always between 0 and 1. It's always positive, but it could be like, I don't know, 10,000. It's a bit extreme, but so how do I interpret that? When probabilities always have to be between 0 and 1, what does it mean when I've got this function that's defining things and it might be more than 1? So remember I said think about it like an interval? And think about your histogram plot where you had a cumulative that's going between 0 and 1. And the bin bin sizes, the frequencies in that histogram plot, you could get numbers that were all over the place if you didn't normalize them. Okay, so here's some example PDF. It's definitely more than one. And let's say I ask you for the probability I get 0.5. How should you think about that? Well, the probability you get 0.5, we've already agreed that it's not about the probability you get 0.5, it's the probability you have a value a little bit around 0.5. So the PDF is telling you if I want the probability I have a value a little around 0.5, so my little around here, this is linked to 0.01. So the height of the PDF, I'm multiplying the height of the PDF times this little interval around 0.5. This height of this PDF here is 0.4, and my interval size is 0.01. So that's one way you could think about this interval. It's approximately equal to the height of the PDF times this little bit around 0.5. Okay, so that's a small probability, but that's a way to interpret the PDF. Think of the PDF as telling you this is the probability I get a value that's a little bit around 0.5. Okay? Okay, and just to state this in general, if I want to calculate a probability, right, here's a probability, here's a random variable, this is two numbers, I'm integrating the PDF between the two numbers, that's interpreted as areas of the curve, which we saw visually. It's exactly equivalent to subtracting the CDF. Very important thing to note. We've agreed that with these continuous things, it makes more sense to be thinking about intervals. So let me ask, if I say, for example, the probability that, think of A and B as, say, 0.2 and 0.3, and X is our RAND function in Excel. So if I want the probability that the RAND function in Excel comes back between greater than or equal to 0.2, less than or equal to 0.3, or strictly greater than 0.2 and less than or equal to 0.3, or greater than or equal to 0.2 and strictly less than 0.3, or strictly greater than 0.2 and strictly less than 0.3, these are all exactly the same. Right? Because any particular point doesn't have any value. So you can be really sloppy with whether you use less than or less than equals to's. Absolutely not true in the discrete case. Right? So in the discrete case, it really matters if I put a little less than or less than equal to. And just to think about it, it's like if I have a die roll, right? And I ask you the probability that you're strictly greater than 1, strictly greater than 1 and less than equal to 2, that is definitely different than the probability you're greater than equal to 1 and less than or equal to 2. Right? So if I say strictly greater than 1 or less than or greater than equal to 1, that really makes a difference. Okay.
So I'm just trying to understand this third bullet point there. So is that because even though A or B are an actual number, because the chances of it being that are like 1 over infinity, that it approaches 0 to the point where you just assume that it's equal to less than equal to, like it doesn't make.
That's exactly right. Okay. You're right on. It's that when we're thinking about the continuous case, the probability of assuming any one particular value, like the probability the stock market returns exactly 4.83569% next year. That's so infinitesimally small that it's like 0. But asking about the probability I get a return between like 4 and 5%, that makes a lot of sense. So that's exactly it, and that's the biggest shift in the thinking. If you've got one thing out of the last 30 minutes, that's the biggest shift in the thinking. Because you're no longer thinking about the die roll, where I roll it, there's a 6 probability it comes up a 1. You're thinking about, well, there's 0 probability it comes up a 1, but it's quite likely it's going to come back between like 0.8 and 1.2. So it's kind of inevitable, as you said, that I am going to talk about integrals sometimes. I am never going to test you on an integral, but I need it sometimes for language, and I'm probably going to use it. I'm not even going to know I'm going to use it, because it's just part of my need. So the two things that I would like to look familiar to you is, if I use this integral sign, this is all immediate area under the curve, and this is just a rule. If it's familiar to you, very good. If it's not familiar to you, you can take it as a rule. if you have an n here, you have something raised to the power of n, this symbol means you return an x to the n plus 1 divided by n plus 1. And here I'm thinking of n as a positive number. I should have said a positive number. So we're going to need to evaluate probabilities. If I'm evaluating some kind of probability, and my PDF function has something like an x to the n in it, that means I'm going to have, this is like the probability I'm greater than or equal to a and less than or equal to b. That's what's going on there with those limits of integration. And, okay, so I remember this rule, so I know I do an n plus 1 here and n plus 1 down there. This notation is telling me that first I substitute b in for x, so I've got b to the n plus 1 divided by n plus 1, minus, second I substitute a in for x. So I will probably do this sometimes. It's going to come up. I'm not specifically testing you on it, but I want to make sure it's not foreign. Does that seem fair? And whenever you see a constant, you can sort of ignore it because it'll just come outside the integral and be multiplied. So I suspect I will also sometimes be loose with my constants. The other thing that's going to come up sometimes is the derivative of an x to the n. So here you just want to remember you bring the n down and you subtract 1 up in the numerator. So this is my rule. Again, constants come out and are multiplied. Just a small bit of practice. What is this guy?
It's that next to it.
Yeah, okay, so page notice, and I'm just going to write this down. Not my pen, but so if I say integral x cubed dx, what's our rule? My n is 2.
X cubed or x squared?
Sorry, x squared. If I say x squared, what's my rule? I add 1 in the superscript, so it's a 2 plus 1 is 3. And down here, I'm dividing by 2 plus 1, which is 3. Okay. And the other one, this is the derivative. What's the derivative of 1/3 x cubed?
X squared.
X squared. So what happened there? I've got a derivative of 1/3 x cubed. Constants come out, so I'll ignore this, and I'll do the derivative of x cubed. And now I use my rule. So I bring the 3 down, and then up there in the superscript I subtract 1. That stuff cancels, so I'm just getting an x squared. And you've also noticed I said something about going from the PDF and the CDF. So you think about that plot. One was a horizontal line, one was the linear, one was the slanted line going from 0 to 1. And one was the PDF, that was this one was the CDF, that was this one. They're sort of back and forth between the two. So this isn't an accident. I just wanted to make the observation that, look, this is x squared. I take the derivative of this thing, I get x squared. I take the integral of this thing, I get x cubed over 3. So they're sort of, in some sense, inverse operations. Okay, so that's just some language that I'm going to need sometime. You'll see it come up here. So if I want to get the expected value of rand, what's the expected value of rand? You know this.
1 over 3.
No, expected value.
0.5.
Average.
0.5.
0.5, yeah. So the mean value of rand, it's coming back between 0 and 1. Everything's equally likely. 0.5 should be that average. Right? Okay. So we agree it's 0.5. How do I see it? If I was going to set it up like this, it's telling me, okay, for expected value, it's x, and the PDF was just 1, so that's what the dx is. And this is basically an average. It's a weighted average. How do I think about it as the weighted average? Well, it's probably easier to think about it here. Remember f of x? I said f of x times a little small value around x. Think that the dx is a little small value around x. This is like the probability that you assume a value close to x. So if you think about it this way, this is like the probability I assume a value close to x. This is x. I'm going to run x over all possible values that this random variable can take on. So that's what this integral is telling you. It's basically telling you to do a weighted average, which is like what you did in the discrete case, but the methodology is a little different. the intuition okay? So we could calculate x squared. If I do that, I gotta use my rule here. We just did it. It's x cubed divided by 3. First I'm replacing it with 1, so that's a third. Second I'm replacing it with 0, so that's 0. So a third minus 0 is just a third. The other two are exactly as we did in the discrete case. I didn't change. This is absolute verbatim. I haven't emphasized this very much, and so I don't think it's going to help us too much. I'm going to ignore that for now. Linearity expectation, this is a helpful rule. It's exactly the same as the discrete. So the biggest change going on here is in discrete cases you see summing, in continuous cases you see numbers. How about variance? So remember, this slide I stole actually exactly from the discrete case. There's nothing that changed. Remember, if we want to calculate variance, we have this formula, expected value of x squared minus ex squared. So I would suggest that's really helpful here. If I want to calculate the variance of this RAND function in Excel, well, ex squared, we just calculated it's a third. This one, mean is a half, I'm squaring it, that's a fourth. So I've got a third minus a fourth, and that's a 12. What's this last one? Oh, and again, this is a rule that you saw exactly in the discrete case. So constants don't have any variance, so that disappeared. If I have a constant multiplying the random variable, it comes outside and it gets squared. Median, what's the median for the spinner example? Should be 0.5. 50% of the time, the RAND function Excel, or my spinner example, 50% of the time that had better be returning something less than 0.5. Okay, so it's got, so this definition you've actually also seen. And for quantiles, so in the spinner example, 25th percent quantile, 25% of the time, if I put a 0.25 there, you're going to get a value that's less than 0.25. Okay, so these definitions actually are exactly like you saw in the discrete case. Okay, so finally we get to Apshop. So now we've seen continuous distributions, and I'm actually going to take this Apshop calculation step by step. So we're first going to do it using a continuous distribution that's uniform, because we've been talking about uniform, and I'm hoping that we feel kind of comfortable with uniform now. And then we're going to take it a step further on Monday, and we're actually going to do this triangular distribution. So we're getting there. So here was Apshop. I'm kind of assuming you remember it. We had this RFP with gain sharing. This is the thing we didn't calculate quite correctly because I gave you a discrete distribution instead of what the case actually gave you. And I'm still going to replace it. The case gave you a continuous triangular distribution, and I'm going to tell you, suppose instead that the savings distribution is uniform with a minimum value of 3.2 and a maximum value of 12.8. So we're getting closer because we've got a continuous distribution. And if I've got a uniform with minimum 3.2 and maximum 12.8, what I'm telling you is every value between 3.2 and 12.8 is equally likely to occur. What's 12.8 minus 3.2? That's 9.6. So if every value between these two is going to be equally likely to occur, that says I'm defining my PDF as 1 over 9.6. And maybe, just to see the picture, so we've got, okay, 3.2 and 12.8, and this is 1 over 9.6, and the PDF is just looking like that. It's a rectangle. Every value is equally likely. The length of this rectangle is 9.6. The height of this rectangle is 1 over 9.6. The area under the curve is 1, or the integral of the whole PDF is 1. Okay. Okay, so this is our step towards continuous triangular. What is the expected value of the RFP bid option? We are ready to do that now. And let's kind of get started a little bit. So I've got this random variable s that represents the savings. This is what I'm telling you to assume is uniform. You're interested in winning bidder's share. I'm guessing this is a little bit familiar. So this is the table. This g of s is basically the function that's the table that you see in the case. It's So it's going from the savings to how much you actually get. And I got one other random variable that I care about, and this is just representing whether or not the bid is won. So 55% of the time you were not getting the bid, and 45% of the time you were. So if you think about what you want to calculate, you want to calculate the expected value of x times y. And x, so x is whether or not you won the bid, y is this winning bidder's present value. So what is winning bidder's present value? Well, it's g of s is given a particular savings, this is the amount I get. I'm discounting it because it's 24 months in the future that I receive it. And this 0.2256 is, remember, I get a $10,000 cash flow stream for the next 24 months. So this is what I want to calculate. And I said first we do the calculation together and second you do it via simulation, but actually the Excel we took a little bit longer than I originally planned, so I think we should go straight to doing it via simulation. And what I posted, what I posted should be something called AppShop Uniform BB. And I've set up the spreadsheet to do it for you. So in this first column B, let's do it here. So in this first column B, I'm going to suggest that you take a sample from the savings distribution. And we know how to take a sample from RAND, that's what we did at the very beginning of class. So we should be able to turn RAND into this uniform savings distribution that I gave you. And I'm doing it for you right here. So RAND, what is this? I'm multiplying RAND by 9.6, 12.8 minus 3.2. So when I multiply RAND by 9.6, this should be giving me a number that's equally likely to come back between 0 and 9.6. And I'm going to add 3.2 because my minimum is 3.2. So when I add 3.2 to it, I'm now getting a number that's equally likely, I'm now shifting it up, it's equally likely to come back between 3.2 and 12.8. So what I can do here is I want to translate between this continuous uniform distribution and what it means in terms of my expected present value of this RFP option. And, you know, I don't know exactly how to do that, because I'm kind of looking at this and I'm like, well, you know, that's kind of going to be an ugly calculation, because I know there's going to be some integrals in it, and maybe I like that, maybe I didn't, but I don't know if I want to exactly do that. So let's see, what is the calculation that I'm doing? Well, okay, so for every observation of this savings, I want an expected value, so I'm going to take an average eventually. So I've got the savings here. In column C, oh, winning bidder's share, that's great. I know that from my table, right? That's basically the table, that's this G function. That's some big if statement that I need to put in here. So I'm going to get a savings sample, then I'm going to take the savings sample to the winning bidder's share. Then I'm going to discount it back by 24 months to know what it means to be now. And then over here, I need to know something about whether or not I won the bid. So over here, I need to do something with uniforms and so 45% of the time, if I put a RAND here, and I put a 1 if it's below 45, a 0 if it's above 45, that means 45% of the time I should be putting a 1 and I won the bid. And if I win the bid, then I'm going to go back and I'm going to get this. If I didn't win the bid, then I'm not going to get it. Okay, so I think that's enough to kind of get you started. Why don't you start working on this? Your goal here is to tell me what is the expected value of this RFP bid option under this uniform distribution for your savings. Is that clear? Okay, and I'm going to wander around, so if you need help getting started, I'm happy.
The G function.
G function.
Just the intervals for the bonus.
Oh.
Yeah.
That.
Yeah.
Oh, okay.
And feel free to talk to each other. I like that.
Ryan, got this? You take this one on the next one.
Yes. Yes.
Can you do maintenance every season or all the shares to do? What was it? It's
Just put a ram with it, like the full ram. And then, yeah, and then this would be, oh, I guess you didn't have to do it columns. This one would be equals if this one wasn't
Oh, sorry.
Maybe you put it in
Yeah,
that
yeah,
one,
yeah,
yeah.
okay, okay.
But I mean, that should be equivalent, it's just that I had it do it in 2 steps, so we didn't.
Sorry.
Yeah.
Cash flow.
It is the, present value
Oh, right,
of
of the monthly.
the $10,000 a month for 24 months.
Sorry.
Yes.
It's going.
Yeah, good. Okay.
It's going.
Better than that.
Yeah. There you go.
Oh, so if you put, equals RAM, uniform RAM, it's meant to be uniform RAM, so we're not maybe. And then here, it's if that's less than 0.45, give it a 1, otherwise you can 0. And if I multiply that column, that's either going to be 0 or something. It's not the only way you can set that up. That is present value of $10,000 for a month for 24 months. Oh, yes, yes, I was assuming.
Which is already present. Okay, that's why it's that bigger, okay.
less than, exactly, exactly.
0.75.
4.45. So less than 4.5 by 1, greater than 9. I didn't actually need 2 columns to do that, but you know, there's some of it. It's, I probably, it looks right.
Just the longest if Stacy.
Otherwise, yeah.
So it's possible for
Yeah.
Oh, yeah. I finished it before I got to class. Weird.
So I just listed it by this. Oh, you did. Oh, no. Well, this cell is just that rank. Oh, you were trying to do it there. Oh, this is what you were trying to do right here when you finish here. No. Oh, you were trying to do this was this. So we're looking at.
Oh, I'm plugging, yes.
Right, but this first you're trying to get
Z times.
okay.
It's plus or minus, but you're using Z times sigma.
Oh, so okay.
And actually, I was just going to introduce it today as the confidence function itself. Somebody want to use the confidence function.
But then the thing is that you can't do that because it's giving you 3 separate numbers.
So now the question is, what's the
Oh,
right estimate? Yes, so that mean NPV should be average. Average. So that more observations, what's going to happen is that confidence is going to get tighter, and you can be more confident that that's close to the true value. Yes, that's it. Press F and dig. So you notice that changes a fair bit. So the question is like, how do you know what's true?
You have more observation things that you get.
Yes, exactly. Correct. Yes. So you can be thinking about this, like there's some distribution in TV, and you don't know what that distribution is. And what you're doing right now is setting yourself up something where you can get the expected values of this unknown distribution. Without actually knowing it. It is. You've just constructed a Monte Carlo simulation. Yes.
Depending on the function, I mean, you can use anything.
You use any function, yeah. But yeah, it's an example of like, you know this one, you want to know that one, but it's not such an easy handwritten calculation. I will in the next half of the semester, and this half of the semester, like everything we do, I mean, we actually don't need Everest to do this, right? We can even produce a histogram plot on Excel, so we can get the full distribution of that. But yeah, the average rate, I'll do it, because I want to add on optimizations, so I'll have more coming in the.
Okay. Are we considering the
Oh, actually, you can just do the standard deviation function yourself. And actually, so I was saying no. The reason is this is a sample from a distribution, but that function is correct. Yeah, it's discrete, and you have every single value that's run. No, it's you're putting it in Z so you divide by square root again. So actually, I'll talk about that in just a minute. So, but if there's a confidence function in Excel, so if you want to kind of get a head start and pick up the confidence function in Excel, we'll talk more about it later in class. In this class, for those of you that are, where are people? I want to get everybody. Yeah, how many are getting a mean present value back? Okay, not. For those of you that are getting a mean present value back, can you start pressing F9? Notice that your observation is fluctuating, and
And my second question, which we'll talk about in about 5 minutes, is, okay, if that observation is fluctuating, what are you gonna actually tell me is your average net present value? For those of you, what I'd like to get everybody to, and I will post my spreadsheet after class, is I don't have it open yet. Okay, so here in the savings column, you've entered, this is your uniform random number. So you've entered the formula that I gave you. Oops. You've entered this guy. C is your long if function. This is corresponding to the table in the case. This is also corresponding to the, oops, wrong way, the G function that I gave you here. Discounted is just, okay, so the winning bidder share here, this is 24 months from now, so we're discounting the winning bidder share according to that formula right there. So it's the discounted of what you receive 24 months from now plus this $10,000 cash flow you're receiving for the next 24 months. What's this uniform in bid 1? So I don't know whether or not I'm going to win the bid. I'm only going to win the bid 45% of the time. So in column E, I'm creating a uniform random variable. I'm just typing equals rand. In column F, I'm saying, well, if E is less than 0.45, give me a 1, otherwise give me a 0. Did I have to do 2 columns to do this? No, I could have done it in 1 column, but, you know. So now I'm multiplying in this last column, I'm multiplying column F, and I'm multiplying times C, the winning bidder share. So column G is giving me 1 value of a present value for this RFP option. So I'd like to get everybody to the point where they're getting column G, and then they're coming up here and they're taking an average of column G. Okay, and then I want to talk a little bit again about everything else. So to think, and actually I'll say a few more things. To think about what are you doing here, right? Every observation of the savings, you're translating it to a present value, right? What you're getting is you're getting a distribution of present values for this RFP bid option, right? So this is a random variable. This value of this RFP bid option is a random variable. It's got a distribution associated with it. That sounds kind of hard to compute. It's a continuous distribution. It's some function of this uniform distribution. But actually computing it sounds kind of hard, right? But what you've got in column G is you've got observations from this unknown distribution. So I can take an average of these observations from this unknown distribution and I can get an expected value of it. Okay, so that's what I'm doing there. So I'd like to get everybody to the point where we've got a mean net present value, and then I got a few more things I want to say. So if you're not there yet, can you just kind of raise your hand and I'll come by? Let's give it like 5 more minutes.
Winning bidder share is the geometric depth. So this should be some long if statement there. I don't think I actually wrote it on the slide. Yeah, that's C5. Don't do that yet. We're not. You're ahead of me. You're ahead of me. So this should be the G function, right? So this is if the savings is between 4 and 6, you're going to get 20% of the savings.
Which one?
Otherwise,
Well, I mean, it's just the part of like the
that's that.
greatest percent.
Yeah.
Yeah.
And actually, do you have it? Yeah. That's perfect because now you can make sure that.
An hour before I
Yes. Yes. Sometimes it's 0. It's either 0 or it's exactly right. Go back up, let's see what it fluctuates. It doesn't look like you have to need it yet. So you want to take an average, so this is the biggest one, average.
Oh,
Oh, that's, why don't you put it up there, because it's going to be a little bit more convenient when it's coming out of this way. Yeah. You should be getting something around like 7.
Yeah, clearly I got mine correct.
So press F9.
Is this from this?
I saw it.
Looks like they have
Is that?
So I think another thing I can do, I'm gonna go ahead and post my spreadsheet right now. Because I realize that probably me debugging individually is gonna take too long, so let me post my spreadsheet right now so we all have the same thing.
Oh,
spreadsheet, so this way we can kind of, you can debug anything that was happening to you, and I can say a few things and make sure we're all on the same page. Is that good? Okay, so observation number 1. If you press F9, every time you press F9, you're getting a new sample of random variables. So you're getting a new sample from rand, which means you're getting new savings. Right? So that means that your mean NPV is fluctuating. Let's ignore those for a second. And what is this mean NPV? You know, let me say this because I think this is kind of important. So I sort of alluded to it a few minutes ago. But what's happening in G, right? So we have a distribution on the savings. We don't know what the savings is going to be. What we care about is the present value of the RFP bid alternative. So we're trying to go from this unknown savings to this present value of the RFP bid alternative. So there's a distribution associated with this present value of the RFP bid. So what we're taking in column G is samples from the distribution associated with the present value of the bid. And what I'm doing over here is I'm asking for the expected present value of that bid. So I'm asking for the expected value of a continuous distribution, and these are my samples from that distribution. So this is a Monte Carlo simulation. So one of the things we're doing in this class is we're getting prepared for doing Monte Carlo simulations. You've just constructed one. What exactly is this Monte Carlo simulation? Well, look, we've got, this is our distribution that we have, but our distribution of interest is over here, right? And I said something a few weeks ago about function of expectation is not the same thing as expectation of function. That can happen in the discrete random variable case. That's absolutely true in the continuous world as well, and that's why we want to do this simulation. So is that good? Okay, so now the question is we're trying to evaluate this RFP bid alternative, and we're noticing that, you know, this fluctuates, and I bet none of you have exactly the same number that I have on this screen. So what do I say? What should be my estimate? What should be 0.9? No, 0.9 is kind of high. 0.75? Maybe. I mean, 0.75 seems a bit better. Okay, so I probably need to not just be giving 0.73 or 0.65. I need to say something about how sure am I that that is really the right thing, right? Yeah?
Can you try data table? Data table?
I could try a data table, but I would suggest that that what I'm really getting is I want a confidence interval. I want to not think about this as a point estimate. I want to think about it as a confidence interval. I want to think about it like, I don't know that it's going to be exactly 0.73, but maybe I know that it's really likely to be between like 0.7 and 0.75. That's how I want to think about it. Okay, so that's what I want to construct. And we're going to talk about confidence intervals a little bit more later, but just for now I want to get the idea of them and what they're used for. This is exactly what they're used for, because it doesn't quite make sense to report that as our mean net present value. It makes sense to sort of report something that tells us, well, how sure are we that that's really it? There's obviously some error in that estimate. So to write the confidence interval, first I just need to get the standard deviation of these samples. So let's take the standard deviation function in Excel. And I want the standard deviation of column G, the net present values. And should I use stdv.s or standard dev.p? S? I should use .s because I do not have every possible present value that can come back to me. These are samples from a distribution. I don't have every possible thing that can happen. Okay, so I'm going to use the Excel confidence function. And so if you do Excel confidence, I'm going to do confidence.norm. We can talk a little bit later about which one is which, so just do confidence.norm so we all do the same thing. Alpha is how sure do you want to be. So I'm going to put it at 0.05, and what 0.05 is saying is that I want to construct an interval such that 95% of the time the actual present value of this distribution is within this interval. So that's my goal. .05 equivalently says 5% of the time the actual thing is outside the zone. The next bit is I need the standard deviation, so that's why I had to calculate this up in cell C4. And the last bit is the size, so the size is the number of observations. So I have 1,000 observations in this sample. So I'm going to put 1,000 in. And I'm constructing an interval about this mean. So this is telling me how much to go above or below. And I really should have started out with equals the mean minus confidence.norm of 0.05 C4 1000. And in the right CI, I'm going to do a plus instead of a minus. Is that good?
Can you say that again?
I'm constructing an interval around this mean. So I'm constructing an interval around this mean NPV that's coming back to me. And so in cell C5, I want C3 minus this confidence. In cell C6, I want C3 plus this confidence. Oh, and you know, I actually put it here. So, oops. This is what I'm entering into C5 and C6. Did that answer the question? Okay, so I'm going to do this in cell C6 also. C equals C3 plus deviation, 1,000. Okay, and now if you press F9 a few times, you'll get some different intervals, but what can you say? So what I know is that 95% of the time, the mean net present value, the expected value of this RFP bid option is going to come in between 0.67 and 0.80. If I want to be more confident, if I want to, let's say, 95% is not good enough, I want 99%. I want 99% of the time, I want to make sure that my mean is within that interval. I can go up here and I can change. Instead of 0.05, it should be 0.01. Okay. So this should be 0.1, and this should be 0.1. Okay. If you're not happy with that interval length, if you're saying, wow, that's too long, how would I make it tighter?
Alpha decrease alpha.
Yeah, one way to do it is I decrease alpha. I say, 99%, come on, that's extreme. So let's say I only need like 90%. So only 90% of the time do I need this. So if I decrease the alpha, this is going to give me a tighter interval. What's another way to do it? More observations. So another thing you're going to see is that if you don't like the interval size, if you say, wow, I really want to estimate this a bit better, this is fluctuating at like, I don't know, at least $100,000 there. Take more observations. So this tells you how many observations. Was 1,000 enough? Maybe not. It's enough if you're okay with this range. It's not enough if you're not okay with this range. So this is how you figure out how many observations do I need. Another thing I want to show you in Excel is when we did the savings, right? We have RAND. I had us produce it. It was pretty easy to go from RAND to this uniform distribution. Excel will also do this for you. So if you need Excel to generate random numbers, go to Data, and go to Data Analysis, and then go to somewhere in Data Analysis, you should be seeing random number generation. And then I'm going to press OK. And you notice there's something that says distribution. So you can actually select several different distributions. So I'm going to select uniform. You'll notice that Excel doesn't actually let you select triangular, so that's not built into Excel. We'll have to talk about that a little bit more on Monday. But it does let you select uniform. So if you select uniform and I say number of variables, this is like the number of columns that I want random variables, samples to come out in. So I'm just going to put 1. Number of random numbers should be 1,000. I'm taking 1,000 observations.
I want them between 3.2 and 12.8, that's my uniform distribution. And my output range here is column B. So if I do that and I say okay, it's going to overwrite existing data, I'm just going to let it overwrite my formula. Notice that Excel has now filled in for you in column B 1,000 observations of savings distributions from this uniform distribution. What's the difference? So these don't fluctuate, right? You can press F9 and the other uniform random variable changes, but this one stays exactly the same. So if you want a situation where every time you press F9 you can get a different sample from the distribution, you want to use rand. If you want a situation where you want to just get your observations and they stay fixed and you do calculations and the rands don't change, you want to use Excel's random number generation. Is that good? Okay. Then there's something I'm going to post that we didn't do in class, but you actually have the tools to do this calculation by hand. So another way we could have done this, and what I will post for you rather than doing it, is we could have calculated this. I gave you that integral of x to the n is x to the n plus 1 divided by n plus 1. This was a uniform savings distribution. That's all you need to know to actually do this expected value calculation. So we could do this. Okay? And, why do I care about doing that? I mean, I might argue that the way I want to do this is to first do my hand calculation, then set up my spreadsheet, then worry about what happens if I have a triangular distribution. So have any of you ever made a mistake on your spreadsheet when you're setting up? I'm sure you guys have never made a mistake. I have made mistakes. So an absolutely excellent way to catch a mistake is to first set up your Monte Carlo simulation with something that you can calculate, which I can calculate it for the uniform. Then make sure, so what's the number? The exact number for the uniform is 0.71. Before I say that, I should check. Yeah, it's 0.71. So the exact number is 0.71. There's no uncertainty than that. That I calculated by hand. I know it's exactly 0.71. So once I know that, I can set my spreadsheet up, I can make sure that I'm getting something close to that, and then, if I don't want uniform, I can go to Excel and I can get samples from a different distribution. If I don't want uniform between 3.8 and 12.8, I can change that. If I want triangular, I can change that. We're going to change that on Monday. And we're going to have high confidence that this spreadsheet is correct, because we compared our spreadsheet to, well, we didn't actually compare our spreadsheet to our hand calculations. You compared it to my hand calculation that I noticed.
You have stock returns. What distribution would you use?
So, okay, so this is, the most common model is a log normal model. It's a criticized model because they say that the tails aren't fat enough. So we are actually going to do an exercise where we fit some stock returns to a log normal model. So that's a half answer, I think. And a lot of people that are, yeah, well, let me leave it at that for now. But and so, okay, so we need to do triangular. That's what's coming. And what did we learn today? How to calculate probabilities and summary statistics for continuous random variables. Next time we want to talk about triangular distribution, and that involves something called the inversion method. So that's what we're going to do. And just a note that I'm slightly updating the syllabus because I was kind of going to do all of this in one lecture, and then I realized doing uniform and triangular would be a bit much, so I split it into two. All the due dates and stuff are the same, it just means the content is, I'm going to change a little bit.
Do you have enough info to finish the homework with those lectures?
Yes.
Okay.
Yes. Yes. So you have enough info to finish the homework at this point, yes. And actually, it's only the last question that's on continuous distribution. So the last question, I'm going to ask you to make a uniform calculation, and that's just to make sure you're comfortable making the calculation. And my intention here is that this homework is, a little bit more problem due. Next homework, I'm going to try to do a casing. So that's kind of how we're going.
Thank you.
Okay.